waste disposal facilities covering all aspects, including fundamental, theoretical, and design. And this is quite crucial to enable a robust infrastructure for clean and efficient management and disposal of waste of all kind. And this is going to be an urgent problem, and already it is, as rapid socioeconomic development across the board. In today's lecture, Dr. Bonaparte promises to be highly interesting and educational, and I'm looking forward to it. So without further ado, I'm going to hand it off to Professor Pack, who will provide a little background on the Jack Hill lecture, and then subsequently Professor Stein Struhl will introduce our speaker. So with that, again, warm welcome to all of you to the 27th Jack Hill lecture.
All right, well, welcome, I think, all of you to our 27th Jack Hill lecture. My name is Ronald Pack, and I'm a faculty member of the Department of Civil, Environmental, and Architectural Engineering. And before we introduce our speaker formally, let me say a few words about Jack Hill. Jack Hill was born in 1912 in New York City, and he received his bachelor degree in civil engineering from New York City University in 1940. During the Second World War, he served in the Army Corps of Engineers in the Pacific, where he rose through the rank from major, and later he became a colonel in the Army Reserve. Then he joined the Bureau of Reclamation Engineering Headquarters in Denver in 1946. While at the Bureau, he earned his MS in 1948 and his PhD in 1956 at CU Boulder. Jack was the chief design engineer at the Bureau when he retired in 1975, and he was for many years regarded as one of the nation's best land engineers. Jack Hill's master's degree was on the prediction of pore pressures in compacted fine-grained soils, and his doctoral work on the investigation of negative pore water pressure. And his study had great impact on the engineering of embankment dams. And this brought great credit to the Bureau and earned Jack an international reputation as an expert in geotechnical engineering. And he was awarded the Department of Interior's Distinguished Service Award in 1965, and he received our college's Distinguished Engineering Alumni Award in 1975. He passed away in March 1992. And with this brief bio of Jack Hill, let me now give the podium to Stein Struhl, our distinguished faculty in geotechnical engineering, and formerly, well, there are so many titles that he has, so let me just skip that.
Well, thank you very much. Well, colleagues and friends, I'm delighted and honored to introduce an old friend, Dr. Rudolf Bonaparte, as we've heard the 27th Jack Hill Memorial Lecture in Geotechnical Engineering. As has been mentioned earlier, Dr. Bonaparte is board chairman at Geotechnical Consultants, Inc. in Atlanta, Georgia. And prior to his current position, Dr. Bonaparte served as president and chief executive officer at Geotechnical for nearly 20 years. Time flies, really. Where he built the company from the ground up, from a startup to the present level of over 1,200 employees. It's amazing. Good heavens. More than 60 offices nationally and 5 other countries. Tell us which the other countries are really well. Find out which. Rudy Bonaparte also finds time to remain academically active. His service as professor of practice in the School of Civil Engineering at Georgia Tech. It should be mentioned that he received his undergraduate degrees in civil engineering from the University of Texas Austin, his MS degree in 1978 and PhD degree in 1981 in civil engineering with geotechnical emphasis from the University of California, Berkeley. Dr. Bonaparte's practice is focused on diverse fields within geotechnical and geoenvironmental engineering. There's really no topic in the field that the company doesn't cover. It seems like you touch on the esoteric and highly basic to the super practical, deep down to high up. He's the recipient of numerous professional awards and prizes, including the American Society of Civil Engineers Opal Lifetime Achievement Award in the field of design, ASE's and the Geo Institute's Terzaghi Lecture Award, and the James R. Crowe's Medal of ASE, and the International Geosynthetic Society's AGS Award, to name a few. He's a fellow of ASE and a diplomat of Geotechnical Engineering. He was elected to the National Academy of Engineering in 2007. On a personal note, I first met Rudy when he was a graduate student and subsequently postdoc at UC Berkeley. And both of us were part of a team working on a NASA research project related to definition of a set of potential experiments on fine and coarse-grained soils. You remember all of that? The main question, how the field of soil mechanics might benefit fundamental understanding related to very low effective and total stress level states in the field, as well as in experiments, which might be conducted in low gravity, specifically microgravity experimental studies in Earth orbit, early space shuttle work. While the studies at times involved highly non-traditional soil mechanics, the team came up with ideas that could ultimately shed more light on physical-chemical forces and mechanisms that normally not factored into conventional geotechnical work, including the influence of van der Waals forces and the like. That being said, please join me in welcoming our 27th Hills lecturer, Dr. Rudy Bonaparte.
Thank you, Professor Stewart. I was going to mention those studies. The report date is 1980. I actually pulled it out. Do you remember it has a green cover?
Green cover, really green cover.
A really green cover. And that's when we first met. And I know for me, I felt an instant liking and respect for you and warmth that even though we don't see each other all that often, it exists today. So, thank you. And I'd like to thank Sheeta for being my host this afternoon and helping me with a few things and all of that. So thank you, and setting all of this up. So thank you very, very much. And I'm indeed honored to be here and to carry on the tradition of the Jack Hill lecture. And it was fun reading about him and learning about him and understanding his great contributions as a dam engineer. The title of my talk is Geotechnical Stability of Waste Fills, Lessons Learned and Continuing Challenges. This is a shortened and updated version of the Terzaghi lecture I gave in 2018. When you give the Terzaghi lecture, it's common to sort of show your connection to Professor Terzaghi in some form or another. So I put this slide together that shows my connection to my three principal academic mentors, Roy Olson at the University of Texas, and Mike Duncan and Jim Mitchell, who at the time were at Berkeley. And I'd also like to recognize another former Terzaghi lecturer, Jean-Pierre Giroux, who I understand is a former Hills lecturer from years ago. In fact, maybe all these folks are Hills lecturers, who I worked with and was my colleague and friend and partner for many, many years at Geosynthetic. And then finally, two other former Terzaghi lecturers, Dave Daniel at the University of Texas and Bob Kerner at Drexel. We partnered over a period of 10 or 15 years on a number of EPA research projects and did a lot of things together, and they were very influential in my career and are good friends.
So the organization of my lecture is pretty simple. Think of it as a timeline. We're going to turn back to the clock to really the beginning of when the U.S. Environmental Protection Agency was promulgating regulations for landfills, and engineering technology for these structures was advancing at a rapid rate. And we're going to look at the number of failures that occurred in that time frame, the mid-1980s to early mid-1990s. We're going to see the lessons that were learned during that period. And there were a lot of lessons learned, significant lessons learned. We're then going to fast forward the clock to the current decade, and we're going to see that failures are continuing to occur. And we'll ask ourselves the question, why? What does it mean? What can we learn from that? What does it say about the state of practice and standard of care for engineering related to these facilities? And we'll conclude with a few observations and recommendations. And why is this topic important? Well, because there are a lot of waste spills in the United States and around the world. Just in the US, there are 2,000 active landfill facilities, thousands of closed landfills, many hundreds of huge coal combustion residual impoundments, mostly east of the Rocky Mountains, many mine tailings impoundments, hazardous waste landfills, radioactive waste landfills, and a variety of things. And then globally, there are many more facilities in the US. So the population of facilities is large, and the worry is that unstable waste fills pose risks to lives, property, and the environment. We've seen that particularly in some of the mine tailings failures in the past few years globally, where hundreds of people have been killed, but also some of the failures we've seen with respect to solid waste landfills. So just as background for those of you that aren't familiar with this area of practice, this is sort of a typical layout for a modern landfill. And what we see here, this is the waste mass, and showing it in gray, and these brown lines are soil, we call it daily cover. And the facility is underlain by a composite liner system. You see that in green and black, and a composite liner is typically made up of an upper geomembrane and a lower compacted clay liner. You see that. And it's overlain by a leachate collection and removal system, or LCRS, which collects the leachate that percolates out of the waste and conveys it to a sump where it's pumped out and sent to a treatment plant. And as you develop a facility, it's common to put an intermediate soil cover on top of the waste for a period of time before you put a final cover system in, which we see here. And the final cover system typically also has a geomembrane, except in some very arid climates, and a low permeability soil area and different things. And then I'm also showing gas extraction oil, because for municipal waste landfills at least, this waste biodegrades and produces methane and carbon dioxide gas. If you don't remove that gas from the facility, pressures build up and it needs destabilizing. Plus the gas is a resource that can be used beneficially. And we'll see a couple of case studies where gas and liquids pressures were part of the root cause of the failure. So when looking at one of these facilities, the geotechnical design engineer needs to be concerned with seismic and static stability for a whole variety of potential failure modes, including failure through the waste mass itself. So there you're very concerned about the strength of the waste. Failure through the waste mass and along liner system interfaces. Failure through the waste mass and foundation soils. And then perimeter stability and something we call liner system and cover system veneer stability, where it doesn't involve the waste mass, but you have liner system or cover system components sliding on each other. We're not going to talk about those today. We're only going to focus on failure modes that involve sliding through the waste. So where we started, we're turning back the clock to the early mid-1980s. And again, this is when EPA first promulgated regulations that led to these systems, these liner systems, and leachate collection systems, and all of those different kinds of things. And we're going to see some of the lessons learned. During that time, there were a whole variety of notable waste fill failures. And I've listed a few of them here. And what I'd like to do is just focus on the three that I've highlighted here. I've got 3 or 4 slides on each, and it will lead us to some conclusions about what we learned during the early stages of this practice area. Just got here today, the dry air is making me a little dry, so if you see me drinking a little or a lot of water, you'll know why. Well, the first case study is Kettleman Hills. This is a hazardous waste landfill in California. In the photograph, we see the landfill cell. The black material is the liner system. And these are back slopes on this cell at inclinations as steep as 2 horizontal to 1 vertical, so fairly steep slopes. We see the waste mass here. And while in an interim configuration, this material slid about 35 feet in this direction here. This was in 1988. And this is the liner system installed under the landfill. And it's quite sophisticated. In fact, at this time, 1988 was probably the most sophisticated liner system ever built in the United States for a landfill. It was designed by a reputable engineer. Quality assurance was conducted by a reputable engineering firm, but it failed nonetheless. And so we see, remember the composite liner I mentioned earlier? This is what we have here, the geomembrane and the clay. And then a secondary LCRS. And if that whole liner system by itself isn't enough, another liner system is stacked on top of it. So this is called a double composite liner system, and it's quite protected. So in early 1988, a year after filling had begun with the waste in an interim configuration at a height of about 90 feet, the waste moved about 35 feet laterally over several hours. And it was a large volume of waste, about 600,000 cubic yards. The forensic investigation, and I should mention our firm was involved in the forensic investigations for all the facilities I'll be talking about today. But the forensic investigation revealed a translational sliding mechanism along the liner system interfaces. So it wasn't through the foundation slug, it was along liner system interfaces. The slippage was observed to be at the interface between the secondary HDPE geomembrane and the secondary compacted clay liner. And here we see the compacted clay liner material exposed. And the geomembrane, the black material, is actually under this geotextile, which is white, so you can't see it. But it was sliding between the geomembrane and the clay that was the seat of movement. And for scale, you can see a couple of workers here to get a sense of the slope. And this was after all the waste was removed, as we were peeling everything back to understand the reasons for the failure. Testing that we conducted showed that the interfaces had peak strength and residual strength, and the residual strengths were quite low. For the compacted clay geomembrane interface, residual strengths were about 500 psf. That's very low in this kind of a site. And the geosynthetic interfaces were also very weak, with the peak strengths measured in terms of friction angles, interface friction angles of less than 10 degrees. Analyses and physical modeling also showed that 3D effects were important, as was progressive failure mechanisms due to the loss of interface strength with deformation. These are just a few of the interface tests that we conducted. These are geotextile against geomembrane and clay against geomembrane. And the important thing to note is that the peak interface resistances for both interfaces occurred at only 0.1 to 0.2 inches of movement. These are quite brittle materials, not much movement at all. And that post-peak, there's a rapid drop-off in strength to the residual values, which are those out here, a couple inches of displacement. So if you're building this huge facility, you have these slick interfaces, and they only need to have movement at the interface of a tenth or 2/10 of an inch to go to their residual values. And that was, in fact, the root cause of the failure. There was a lack of understanding of this interface behavior. And so this case history really brought that to the attention of the profession. This just shows a cross-section through the waste fill. So what did we learn with this case study? First, that many liner system interfaces are weak and exhibit pronounced shear softening with residual strengths much lower than peak strength. We know that well now. We didn't know that so well in 1988. Liner system construction and waste placement by themselves can induce movements that cause those interfaces to go to the residual strength value. So it's almost like, in some circumstances, you would have a hard time building the structure without inducing the residual strains. And so the design process needs to reflect that. And in fact, in response to that, material manufacturers started to think about new materials that could get past that. And so today we have things like textured geomembranes. I'm sure some of you are aware of that, and different materials that are intended to overcome these obstacles. Waste mass stability evaluations need to address all interim waste billing configurations. This facility failed at an interim configuration, not in the final configuration, so one needs to be cognizant of that. And we learned, because of the large amount of testing on this project, that geomembrane compacted clay interface strains are sensitive to their moisture density and shearing conditions. So you don't want to compact them too wet. You don't want to induce a whole lot of shearing during the compaction, so you get a remolded structure. But the problem with that is that CCL compaction conditions to get high interface strains work against the compaction conditions to get a liner that performs best from an environmental perspective. So I think we all know that if you want a low permeability compacted liner, you compact wet of optimum with kneading compaction, smooth rolling the surface. Those create weak interface conditions. So you have this push and pull in the design process that we know today we need to balance out as part of the design. The second case study is a year later. This is in Maine. This is a waste mass and foundation soil failure. Obviously, this is the landfill cell that failed. And you can get a sense, if you look at this carefully, that the failure started here on the west side of the site and retrogressed as a series of slide blocks, as we see, back to the east side of the site. This was about an 8-acre landfill sitting on a foundation of very sensitive glacial marine clay silt. It had an over-consolidated crust, so strong soil crust that transitioned at a depth of about 20 feet to a normally consolidated state. The clay silt served as the liner system. There was no constructed liner system in this case. So the landfill was filled over a period of about 13 years. And when it reached a height of about 70 feet, and after a period of heavy rain, a rapid retrogressive slide occurred involving about 650,000 cubic yards of material. So again, a rather large slide and a rather fast failure, a minute. The forensic investigation found that the slide surface was in the normally consolidated zone of the clay silt below the over-consolidated crust. And while it's not completely obvious in the photograph, the movement of these blocks was over 150 feet from east to west, so you get a sense that this clay silt layer liquefied as it filled. It's very sensitive. You'd expect that. Is that kind of what these sensitive clays do, Professor Stewart?
Yes.
Those Norwegians know this stuff. So, and these waste blocks slid on that. So, when the landfill was first designed, the engineers did some vein shear testing and did some slope stability analysis, and then they went along for 13 years. And at some point, the owner wanted to go higher and thought we should probably do some more analyses. So, some updated slope stability analyses were conducted where the engineers tried to estimate with just a few piezometers the degree of consolidation of the foundation, estimate shear strengths using a Shan-Step method, and with that approach, came up with a factor of safety for the landfill of 1.0. So you would think they would stop filling the landfill, right? You would think. They didn't. They did some things. Oh, I should also mention that they had, I think, 2 or 3 inclinometers around the property, and they were measuring about 1.5 kilometers of movement a month in the soft zone, and they characterized that as a high rate of movement but acceptable. So site operations continued, and stabilizing tow berms were installed around the edge of the landfill. So that's a good thing. They put in stabilizing berms. But they didn't put in stabilizing berms on the west side. It's really interesting why they put stabilizing berms in on the west side. Because on the west side, they were making a 6 foot deep excavation along the entire toe of the landfill for construction of a new mine cell. So think about it. You don't put the berm in, and moreover, you make this excavation. This is the strongest material you have on the site. It's a silver consolidated crust. You're removing it, you're also removing the weight, the counterbalancing weight. And so with that material removed, the toe of the landfill on the west side caused a localized failure of the glacial marine clay silt. And once that initial failure occurred, the sensitive material just started collapsing and retrogressed back across the entire site. The forensic investigation, I was going to skip this, but it's interesting. The forensic investigation showed that the landfill was indeed at a factor of safety of 1.0, but for all the wrong reasons. In these updated slipability analyses, the shear strength of the waste was underestimated by about 25-30%, so it's 25-30% stronger than they had predicted in these updated analyses. But they underestimated the unit weight of the waste by 25 or 30%. And those were counterbalancing problems. They also didn't measure pore pressures in the landfill, and we determined afterwards that there were quite elevated pore pressures in the fill, which had a destabilizing effect. This is pretty much drawn to scale. You can see the original configuration of the landfill across the excavation in these blocks after the failure. So what did we learn here? Both waste and foundation unit weights and shear strengths must be adequately characterized. And I think for a long time we took unit weight of waste kind of for granted. It really didn't get much attention. This case study showed it needed to have attention. A clear understanding of the liquid levels and pore pressures in the fill are important for the satisfactory assessment of stability. That seems pretty obvious. And each significant construction and or operational change in the field should be evaluated prior to implementing that change. In this case, the excavation at the toe was clearly a triggering mechanism for this failure. And I don't believe, could not find any information anywhere when we did the investigation, that that was actually evaluated as a potentially critical stability condition. And finally, for soft soil sites, the rate of waste filling may need to be limited by the rate of foundation consolidation. So this is a classical stage construction consolidation problem. It's just like if you're building a highway embankment or any other kind of structure on a sub-foundation. You can't build faster than the strength of the foundation allows you to build. And if it's consolidating and gaining strength, then your filling schedule needs to be in harmony with that. The third case study is the Rumpke municipal waste landfill failure in Ohio in 1996. And this is another waste mass and foundation cell failure, but a little bit different one. This is a very large landfill. This is the original toe of the landfill, this yellow line. So the area that failed is all above that yellow line. This is about a 20-acre area. Gives you a sense of the scale of this facility. And you can see that the headscarp up here, and then the movement of this waste. It looks like it almost liquefied and flowed more than 1,000 feet here in a downslope direction. So a very large slide. And the story with this facility is that starting in the 1940s, this family named the Rumpkes started dumping waste right into a ravine on their property. They found that was the way they could make some money. And this ravine happened to be lined or underlain by clay, colluvial, and residual soils that form the mantle of the bedrock. And I highlighted that because that's important to this case study. Landfilling continued to the failure to grades exceeding the permitted grades for the facility. So you have a permit, the regulators say you can fill to 100 feet, let's say, and if you fill above 100 feet, you're filling past your permit limits, and that's not acceptable. They were filling past their permit level limits at this site. The week prior to the failure, tension cracks were observed at the top of the landfill at the eventual location of this head start. Not a good sign. The morning of the slide, the toe of the landfill began to move, and the tension cracks at the top of the slide began to widen. The operator had the good sense to move everybody back, and there were several hours of progressively increasing creep rates. It was clear that the landfill was on the verge of failure. When it failed, it did so quickly over a period of about 5 minutes, starting at the toe and retrogressing back to the headscarp area that we see. In that short time, about 1.5 million cubic yards of material slid into an adjacent excavation. The excavation was being made for a new line cell. It wasn't one of the root causes of the failure, but it is one of the reasons the waste moved so far, converting all that potential energy into kinetic energy as it moved down the slope. So here is a kind of an idealized cross-section through the landfill at a critical section. You see the MSW and the native bedrock and then the native brown soil here. And so, as I mentioned, due to delays in opening the lateral expansion, the owner overfilled the site by about 30 to 40 feet. So this darker brown waste is material he shouldn't have placed. And he placed it to a higher elevation and at a steeper slope than his originally permitted landfill. The forensic investigation showed that the slip surface extended at a near vertical angle through the waste. This is the headscarp area you see in the photographs, down to the native soil layer, and then along the interface out to the toe. The investigation also showed that there were likely leachate levels in this fill of about 30 to 40 feet at maximum that were not being considered by the owner prior to the failure. So some things that were not too good in this case. We conducted post-failure testing of the native soils, and that testing produced fully softened and residual shear strength, effective stress friction angles for the materials of 20 and 8 degrees respectively. And when we did back analyses to calculate a mobilized friction angle at the incipient failure, the start of failure for the slope, we estimated a value of about 12 degrees. So this material, this native soil, had clearly, through weathering over the years, moved towards its fully softened shear strength. And then either through original filling of the cell or the overfilling, coupled with the pore pressures and other things, it drove enough deformation along that native soil layer to drive the interface shear strength lower to a point at which the slope fell at a friction angle on the order of about 12 degrees. Skip that. So what were some of the lessons from this case study? Foundation conditions for old unlined waste fills must be thoroughly understood if additional filling, excavation, or expansion of the fill is planned. Here they just kept stacking waste. They didn't say what are the implications of doing that, and that was an error. Straining compatibility between